Hi guys, so today's physics review is all about energy and work. So what is work? Work is the force acting on an object to cause a displacement. There must be displacement or else no work has been done. Like if you move a book 3 meters to the right and then move it right back to where it originally was, technically no work has been done because there was zero displacement. Force and displacement also have to be in the same direction. For example, if a force is acting vertically on an object and the object moves 3 meters up and then 2 meters to the right, only the vertical 3 meters counts towards the work, and this is because work depends on displacement in the direction of the force. Also, the formula for work is work equals force times direction, and the units are joules. Now, power is the rate at which work is done, and the formula is power equals work over time, and the units are watts. Now, moving on to energy. So energy is the ability to do work, and energy is work because the work you put into a system is equal to the energy that the system gains, and energy is also measured in joules. Now, moving on to specific types of energy, we have potential energy, which is stored energy. For this unit, potential energy will just be like gravitational potential energy, which is the energy an object has stored based on its vertical position. So height is very important. And the formula for this is potential energy equals mass times gravity times height. And work is equal to the change in potential energy. Now, kinetic energy is the energy of motion, and the formula for this is kinetic energy equals 1/2 times mass times velocity squared, and work is equal to change in kinetic energy. Now, conservation of energy is a huge concept that you need to understand. So basically, the total energy of a system will always be constant because energy cannot be created or destroyed. But energy can be changed from one form to another. For example, as an object falls, its potential energy is converted into kinetic energy. Also, sometimes energy is lost and turned into heat or like a non-conservative kind of energy. So non-conservative forces like friction can convert mechanical energy into heat or other forms of energy, which are not recoverable for mechanical work. By the way, mechanical means kinetic plus potential, if you forgot that. But the total energy of the system, including these losses, still remains constant, and the formula for when this happens is potential energy plus kinetic energy plus Q, which is any other form of energy, is equal to total energy. Now, another big concept you need to know is pendulums. So pendulums are those things with the ball, and when you release it, it swings back and forth, right? So basically, at the point of release or the highest point, the pendulum's potential energy will be at its max, and there will be no kinetic energy. But once the pendulum reaches its lowest point, all that potential energy has been converted into kinetic energy. So at the lowest point, there will be zero potential energy, and kinetic energy will be at its max. Now, the last thing you need to know is springs. So we have force on a spring constant, and change in spring length. And you could solve for any of these using the formula force on a spring equals spring constant times change in spring length. And finally, we have elastic potential energy, which is once again used for springs. So this is the energy stored in a spring or any kind of elastic item, and the formula for this is elastic potential energy equals 1/2 times spring constant times change in spring length squared. Now let's do some multiple choice. Number 1, how long would it take a machine to do 5,000 joules of work if the power rating of the machine is 100 watts? So this question is asking us for time, and it gives us both work and power. In order to find time, we need to plug these values into the power formula and then solve. So power equals work over time. So power is 100 watts, that equals 5,000 joules over time. So if we solve for time, we're gonna get 50 seconds. Number 2, a pendulum is pulled to the side and released from rest. Which graph best represents the relationship between the gravitational potential energy of the pendulum and its displacement from its point of release? So remember, when a pendulum is at its point of release, aka its maximum displacement, the potential energy is at its max and there's no kinetic energy. Once you release it, the potential energy begins to be converted into kinetic energy, and once the pendulum reaches equilibrium or zero displacement, there's going to be no potential energy, and kinetic energy is going to be at its max. As it completes its swing and rises back to maximum displacement, potential energy once again reaches its maximum, while kinetic energy is back to zero, which is why D is our answer. Number 3, the total work done in lifting a typical high school physics textbook of vertical distance of 0.1 meter is approximately what? So all these answers have like 1 and 5, so we can assume that the weight of the average textbook is going to be 1.5 kilograms. Now, in order to find work, we need to find the force of the book first. So force equals 1.5 kilograms times 9.81 meters per second squared, which is 15 newtons. Now work equals force times distance, so 15 newtons times 0.1 meter is equal to 1.5 joules, which is B. 4. The potential energy stored in a compressed spring is the change in the spring's length as the kinetic energy of a moving body is to the body's what? So this question is comparing potential energy of a spring and kinetic energy. So for this, we should write out both formulas of the energies. So potential energy of a spring equals 1/2 kx squared, and kinetic energy equals 1/2 mv squared. So if you see here, the potential energy of a spring and kinetic energy formulas are very similar. They have the same format, but the only difference is that potential energy of a spring uses spring constant and change in spring length, whilst kinetic energy uses mass and velocity. For PES, change in spring length is being squared, while for KE, velocity is being squared. So this means that change in spring length and speed or velocity have the same relationship to their respective formulas, which is why the answer here is going to be speed. Number 5, a 40-kilogram student runs up a staircase to a floor that is 5 meters higher than her starting point in 7 seconds. The student's power output is what? So this question is asking for power, so we need to use the power formula. We have time, but we do not have work. The work formula is work equals force times distance, and we have distance but not force. So to find force, we just have to do mass times gravity, so 40 kilograms times 9.81 meters per second squared equals 392.4 newtons. So we can plug that in to find work. So work equals 392.4 newtons times 5 meters, which is 1,962 joules. And now we can plug this into power. So power equals work over time. So 1,962 joules over 7 seconds equals B, 280 watts. 6. As the time required to do a given quantity of work decreases, the power developed what? So let's write the power formula again. So P equals work over time. Now you can see that if we decrease time here, power should increase because there's an inversely proportional relationship here. So time is in the denominator, so when you decrease the denominator, the quotient increases. So that's why it's going to be answer B. 7. A horizontal force of 5 newtons acts on a 3-kilogram mass over a distance of 6 meters along a horizontal frictionless surface. What is the change in kinetic energy of the mass during its movement over the 6-meter distance? So this question might seem a bit confusing, but remember that total work done on an object is equal to change in kinetic energy. So instead of using the kinetic energy formula, we don't have velocity, we can just use the work formula instead. So work equals force times the distance, and that's just going to be 5 newtons times 6 meters, and that's equal to 30 joules. So our answer is going to be choice D. Number 8. The diagram below represents a 155 Newton box on a ramp. Applied force F causes the box to slide from point A to point B. What is the total amount of gravitational potential energy gained by the box? So gravitational potential energy is really easy. We just use the formula PE equals mass times gravity times height. And they already gave us mass times gravity as weight, so we just do 155 newtons times 1.8 meters, and that gives us choice A. 9. The gravitational potential energy with respect to Earth that is possessed by an object is dependent on the object's position. So position just means height, and remember that potential energy is directly dependent on height. Number 10. An unstretched spring has a length of 10 centimeters. When the spring is stretched by force of 16 newtons, its length is increased to 18 centimeters. What is the spring constant of the spring? So this question gives us force on a spring, change in spring length, and we need to find spring constant. With these values, we can use the spring force formula and then plug in to solve for spring constant. So Fs equals Kx. It tells us that Fs is 16 newtons. We're solving for K. And change in spring length, it starts at 10 centimeters and it goes to 18 centimeters. So it changes by 8 centimeters. So it's times 8 centimeters. If we solve for K, we're going to get 2. So our answer is 2 newtons over centimeters. Number 11. As shown in the diagram below, a child applies a constant 20 Newton force along the handle of a wagon which makes a 25-degree angle with the horizontal. How much work did the child do in moving the wagon a horizontal distance of 4 meters? So don't get tricked here, guys. It tells us that the child applies a force of 20 newtons, right? But that's like the total force. Since the wagon is being horizontally displaced by 4 meters, our force needs to be horizontal as well. So we need to find only the horizontal component of this 20 Newton force. So we can do this by using cosine to calculate this adjacent value here. So cosine of 25 degrees equals opposite over, adjacent over hypotenuse. So x over 20 newtons. So x is going to be 18.1 newtons. And now with this, we can solve for work. So work equals force times distance. So 18.1 newtons times 4 meters equals 73 joules. Number 12. A pendulum is made from a 7.5 kilogram mass attached to a rope connected to the ceiling of a gymnasium. The mass is pushed to the side until it is at position A, 1.5 meters higher than its equilibrium position. After it is released from rest at position A, the pendulum moves freely back and forth between the positions A and B, as shown in the diagram below. What is the total amount of kinetic energy that the mass has as it swings freely through its equilibrium position? So as we discussed earlier, the change in potential energy and change in kinetic energy of a pendulum are equal. And this is because potential energy is converted into kinetic energy as the mass reaches equilibrium and then is converted back into potential energy when it reaches its max height again. So even though we don't have the necessary values to use the kinetic energy formula, we can just use the potential energy formula instead, since total potential energy is equal to total kinetic energy. So the formula for potential energy is PE equals mass times gravity times height. So 7.5 kilograms times 9.81 meters per second squared times 1.5 meters. And that's going to give us 110 joules. 13. What is the maximum amount of work that a 6,000 watt motor can do in 10 seconds? So this question is easy. We have power and time and we need to find work. So we just plug in to find work. So power equals work over time. 6,000 watts equals work over 10 seconds. And we solve for work. Work is going to be 60,000 or 6 times 10 to the 4th joules. 14. A 110 kilogram bodybuilder and his 55 kilogram friend run up identical flights of stairs. The bodybuilder reaches the top in 4 seconds while his friend takes 2 seconds. Compared to the power developed by the bodybuilder while running up the stairs, the power developed by his friend is the same. So let me explain what's the same. If you think about it, the bodybuilder has twice the mass of his friend because his friend is 55 kilograms while the bodybuilder is 110 kilograms. And also, the bodybuilder takes twice the amount of time because his friend takes 2 seconds while he takes 4 seconds. Now, remember that power equals work over time, or we could also write this as, mass times gravity times displacement over time. Now, since they both have the same gravity and displacement, we're just not going to look at these two factors. We're only going to look at mass over time. Now, notice these proportions, 55 over 2, 110 over 4. They're the same thing, which is why they develop the same power. 15. The diagram below shows block A having a mass of 2m and a speed of v, and block B having a mass of m and a speed of 2v. Compared to the kinetic energy of block A, the kinetic energy of block B is what? So for this, I'm going to write out the kinetic energy formula. So Ke equals 1/2 mv squared, And what we have to do is we just plug in for both blocks. So block A has a mass of 2 kilograms and it moves 1 meter per second squared. So that's going to equal 1 joule. Now block B, I'm going to write it down here. So block B is 1/2 times a mass of 1 kilogram and a velocity of 2 meters per second squared, and that's 2 joules. So that means block B is going to have twice the kinetic energy of block A. So that's choice B. 16. A block initially at rest on a horizontal frictionless surface is accelerated by a constant horizontal force of 5 newtons. If 15 joules of work is done on the block by this force while accelerating it, the kinetic energy of the block increases by what? So remember that work is equal to change in kinetic energy. So if 15 joules of work was done on the block, then the kinetic energy of the block was also increased by 15 joules. 17. The diagram below shows a 5 kilogram mass sliding 9 meters down an incline from a height of 2 meters in 3 seconds. The object gains 90 joules of kinetic energy while sliding. How much work is done against friction as the mass slides the 9 meters? So this question is talking about work done against friction. So friction plays a role in this because it can convert energy from the system into some other kind of non-mechanical form of energy. As a result, total mechanical energy is reduced. So we know that the object gains 90 joules of kinetic energy once it's finished sliding down the incline. To determine how much energy the system initially had, we have to solve for potential energy. So potential energy equals mass times gravity times height. So 5 kilograms times 9.81 meters per second squared times 2 meters equals 98 joules. So 98 joules, the initial, and 90 joules, which we had final, means that 8 joules of work was done against friction. So that's choice D. 18. A 75 kilogram bicyclist coasts down a hill at a constant speed of 12 meters per second. What is the kinetic energy of this bicyclist? So, this is an easy question. We just solve for kinetic energy using the formula Ke equals 1/2 mv squared. So Ke equals 1/2 times 75 kilograms times 12 meters per second squared. And once we solve for this, we're going to get 5.4 times 10 to the third joules. 19. At what point in its fall does the kinetic energy of a freely falling object equal its potential energy? So kinetic energy and potential energy will always be equal when the falling object is halfway. So when the object is at its start, there's going to be, potential energy is going to be at its max, right? And there's going to be no kinetic energy. Now, when it's halfway, they're going to be equal to each other. So PE equals KE. And once it reaches its end, there's going to be 0 PE and max KE. 20. A spring gains 2.34 joules of elastic potential energy as it is compressed 0.25 meter from its equilibrium position. What is the spring constant of the spring? So for this question, we need to solve for spring constant using the elastic potential energy formula. So PES equals 1/2 kx squared. So 2.34 joules equals 1/2 times K, which we're trying to find, times 0.25 meter squared. And when we solve for K, we're going to get 74.9 newtons over meter. 21. The diagram below shows a 50 kilogram crate on a frictionless plane at angle theta to the horizontal. The crate is pushed at a constant speed up the incline from point A to point B by force F. If angle theta were increased, what would be the effect on the magnitude of force F and the total work W done on the crate as it is moved from point A to point B? So if we increase the angle of this incline, that means the height of the crate will increase as well. So an increase in height results in more gravitational potential energy, and since change in potential energy and work are equal, that means work will increase. So since work has to increase, that's how we know options B and C are incorrect. Now, since work has a direct relationship, work and force have a direct relationship in the work formula, so work equals force times distance or displacement. If work increases, then force has to increase as well, which is why choice A is correct. 22. Which graph best represents the relationship between the elastic potential energy stored in a spring and its elongation from the equilibrium? So the formula for elastic potential energy is PES equals 1 half kx squared. So if we look at change in spring length, which is x squared, we can specifically see here that not only is there a direct relationship, but it is squared. So our graph has to be exponential. So if elongation increases, then elastic potential energy will also increase exponentially. So it can't be A, it can't be B, it's going to be C. 23. As shown in the diagram below, a student exerts an average force of 600 newtons on a rope to lift a 50-kilogram crate a vertical distance of 3 meters. Compared to the work done by the student, the gravitational potential energy gained by the crate is what? So we're comparing the crate's potential energy and the work done by the student. So let's solve for both. For the crate, we just have to use the potential energy formula, which is PE equals mgh. So 50 kilograms times 9.81 meters per second squared times 3 meters. And that is going to be 1,471.5 joules. And now let's solve for the student by using the work formula. So work equals force times distance or displacement. So 600 newtons times 3 meters, and that equals 1,800 joules. So comparing these two values, we can see that the difference here is 330 joules. So our answer is B. So now I'm going to skip around to some more difficult questions. So I'm going to skip these two and move on to number 26. So the diagram below shows a toy cart possessing 16 joules of kinetic energy traveling on a frictionless horizontal surface toward a horizontal spring. If the cart comes to rest after compressing the spring a distance of 1 meter, what is the spring constant of the spring? So don't get tricked by this question. It gives us kinetic energy, but in this scenario, kinetic energy and elastic potential energy are the same. So in order to solve for spring constant, we can just use the elastic potential energy formula. So Ke equals PES in this situation. So PES equals 1 half kx squared. So 16 joules are kinetic energy, equals 1 half times K times 1 meter squared. So K is going to equal 32 newtons over meters. 28. Which graph represents the relationship between the gravitational potential energy, GPE, of an object near the surface of Earth and its height above the surface of Earth? So the formula for potential energy is mass times gravity times height. So if the height of an object increases, then the potential energy will directly and proportionally increase along with it. So our answer here is going to be D. So this is going to be our last multiple choice question, so 32. In the diagram below, an ideal pendulum released from position A swings freely to position B. As the pendulum swings from A to B, its total mechanical energy remains the same. So remember that mechanical energy is potential energy plus kinetic energy. So mechanical energy is basically just the total energy of the system. Throughout the swing of the pendulum, total mechanical energy does not change due to conservation of energy. The total energy of the system does not change, it just converts between kinetic and potential. Okay, so now let's do some short response. So number 1, a 1.7 kilogram block slides on a horizontal frictionless surface until it encounters a spring with a force constant of 955 newtons per meter. The block compresses the spring by 4.6 centimeters before turning around and sliding in the opposite direction. Find the initial speed of the block. So this question gives us spring constant and change in spring length, and since we're working with the spring, we should just obviously find elastic potential energy first. So elastic potential energy equals 1 half kx squared. So 1 half times 955 Newton per meter times 0.046 meter squared. And that equals 1.01 joule. Also, sorry, I forgot to show the conversion, but 4.6 centimeter equals 0.046 meter. Okay, so now that we have elastic potential energy, we need to find a way to turn elastic potential energy and get velocity. So what other form of energy has velocity in its equation? That's going to be kinetic energy. So initially the block is sliding on the surface and its energy is only converted into elastic potential energy once it's compressed by the spring. This means that initially its energy was in the form of kinetic energy. Also, due to conservation of energy, we know that the value for final elastic potential energy, which we just solved for, is going to be the same as the value of initial kinetic energy. So in order to solve for velocity, we can just plug in what we know to the kinetic energy formula. So kinetic energy equals 1/2 mv squared. So 1.01 joule equals 1/2 times 1.7 kilogram. We're trying to solve for velocity squared. Once we solve this out, we're going to get a velocity of 1.1 meter per second. And that's going to be our final answer. Number 2, Sophie has a mass of 52 kilograms. She rides up the escalator at the mall. The escalator has a length of 227 meters and an average inclination of 31 degrees. How much work does the escalator do on Sophie? So, in order to solve for work, we need to know Sophie's displacement. It tells us that the escalator has a length of 227 meters, but this is not the length that we are going to use. Remember that for work, force and displacement have to be in the same direction. In this problem, it does not state that there's any external horizontal force being applied to her, but since the escalator is doing work to lift Sophie up, that is going against gravitational force, which acts in a vertical direction. So for this problem, since force is vertical, we're only looking for vertical displacement, which is going to be this. So we need to find her vertical displacement. And we just have to find the vertical component of the elevator's length. And we can do this by using sine. So sine is opposite over hypotenuse. So sine of 31 equals x over 227 meters. So if we solve for this x here, we're gonna get 116.9 meters. So this is 116.9 meters. So now that we know the vertical length of her movement, we need to solve for work. So remember that work is equal to energy, so instead of using the work formula, we can just use the potential energy formula. So potential energy equals mass times gravity times height. So potential energy equals 52 kilograms times 9.81 meters per second squared times 116.9 meters. We calculate this, we're going to get 59,633.03 joules, or you can just round that to 60,000 joules, and that's our final answer. Number 3, a student librarian picks up a 2.2 kilogram book from the floor to a height of 1.25 meters. He carries the book 8 meters to the stacks and places the book on the shelf that is 0.35 meter above the floor. How much work does he do on the book? So this question seems kind of tricky, but it's really not. Remember that we're focusing on displacement. So in the end, the book only has a displacement of 0.35 meter. And we're not going to do anything with the 8 meters that was moved horizontally because the force on the book is once again just gravity, which is vertical. So we're only looking for vertical displacement. So now we can just solve for work by using the PE formula because work is equal to potential energy. So potential energy equals mass times gravity times height. So 2.2 kilograms times 9.81 meters per second squared times 0.35 meter. And we're going to get 7.55 joules. So this is going to be our last question for today. So number 4. Deep in the forest, a 17-gram leaf falls from a tree and drops straight to the ground. If its initial height was 5.3 meter and its speed on landing was 1.3 meters per second, how much non-conservative work was done on the leaf? So this question is asking for non-conservative work. And if you forgot what that was, it's basically just other forms of work. So like when this leaf falls to the ground, if its final kinetic energy is different from its initial potential energy, that means that some of that energy got converted into something else. So for this question, we're just going to solve for the potential energy of the leaf before it fell, and then the kinetic energy once it hit the ground. So first thing we're going to do is we're going to solve for the potential energy. So potential energy equals mass times gravity times height. So 17 grams is equal to 0.017 kilograms. So 0.017 kilograms times 9.81 meters per second squared times 5.3 meter. And that's going to equal 0.88 joules. Now let's solve for kinetic energy. So kinetic energy equals 1/2 mv squared. So 1/2 times 0.017 kilogram times 1.3 meters per second squared. And that's going to equal 0.014 joules. So obviously there's a huge difference between these two numbers. So in order to solve for non-conservative work, we're just going to find the difference between these values. So 0.88 joule minus 0.014 joule is equal to 0.87 joule. But we're going to make this value negative because it was friction that slowed the leaf down. So negative 0.87 joule is our final answer.